invertible residual networks. And this is from the guys that came up with the neural ODE, Duvenod and Rikichin. Grathwell, I think, was also part of the team. Henry Jacobson as well. Yeah. So one of the problem or one of the, I think, the assumptions for neural ODEs or the way it works is that you integrate forward from a certain point, from a certain xt, you integrate forward to xt plus capital T, right? And for back propagation, you integrate backwards. So going back from the same point, so you get the gradients, and the gradients get you to a point, and you integrate backwards, and you say, okay, I want so you there's the, let's say there's the error, right? There's error associated here, and you integrate backwards, and it's supposed to you integrate the error backwards. Yeah, and one of the key assumptions is that integrating forward to one point, and from that point integrating backwards takes you to the same point. So there is one-to-one correspondence between one point in the future and one point in the present, or x of t and x of t plus capital T, meaning that any integration that happens is basically an invertible function. Invertible functions, if you have the domain and codomain, in order to have invertible functions, all the elements in the codomain should get mappings to them, and so all the elements in the codomain should get mappings, and no two elements on the source domain map to the same element in the codomain, right? Because otherwise, when you go back, do you go back to this one or this one? So if there is one-to-one mapping, it's a bijective map, then you get invertibility. So here's the problem. How can we... Well, there is... invertibility comes up for many applications. When you want density estimation, basically you have finite probability amount, and you want to distribute this probability to items in the codomain, and basically you want you estimate the probability density for this guy based on the amount of probability density taken from the source domain. And only if there is one-to-one mapping between the items in the domain, then you can say, yeah, this density is the same as this one because it's allocated entirely for this, and nobody else shares this density. Okay. So starting with the paper, Invertible Residual Networks, abstract. We show that standard ResNet architectures can be made invertible, allowing the same model to be used for classification, density estimation, and generation. Typically, enforcing invertibility requires partitioning dimensions or restricting new network architectures. In contrast, our approach only requires adding a simple normalization step during training, already available in standard frameworks. Invertible ResNets define a generative model which can be trained by maximum likelihood on unlabeled data. To compute likelihoods, we introduce a tractable approximation to the Jacobian log determinant of a residual block. So this is basically tracking how the density in one is being diffused into to other sorts to other parts of the codomain. To compute likelihoods, we introduce a tractable approximation to the Jacobian log determinant of the residual block. Our empirical evaluation shows that invertible resonance perform competitively with both state-of-the-art image classifiers and flow-based generative models, something that has not been previously achieved with a single architecture. Okay, compelling abstract. Introduction. One of the main appeals of neural network-based models is that a single model architecture can often be used to solve a variety of related tasks. However, many recent advances are based on special-purpose solutions tailored to particular domains. State-of-the-art architectures in unsupervised learning, for instance, are becoming increasingly domain-specific, and they cite a lot of papers. On the other hand, one of the most successful feed-forward architectures for discriminative learning are deep residual networks, which differ considerably from their generative counterparts. Really? I thought resonance are also very popular in GANs, in the generator part of the GANs. This divide makes it complicated to choose or design a suitable architecture for a given task. It also makes it hard for discriminative tasks to benefit from unsupervised learning. We bridge this gap with a new class of architectures that perform well in both domains. Well, there is also the question whether, like, you're restricting the class to be bijective, where we know that resonance or neural networks in general can take on or can approximate any function, not just bijective ones. You're saying that bijectives are more suitable? That's, I don't know. To achieve this, we focus on reversible networks, which have been shown to produce competitive performance on discriminative and generative tasks independently, albeit in the same model paradigm. They typically rely on fixed dimension splitting heuristics, but common splittings interleaved with non-volume conserving elements are constraining, and their choice has a significant impact on performance. This makes building reversible networks a difficult task. In this work, we show that these exotic designs, necessary for competitive density estimation performance, can severely hurt discriminative performance. To overcome this problem, we leverage the viewpoint of resonance as an Euler discretization of ODEs, and prove that invertible resonance, Iresonance, can be constructed by simply changing the normalization scheme of standard resonance. As an intuition, Figure 1 visualizes the differences in the dynamics learned by standard and invertible resonance. Okay, standard resonant and invertible resonant. Dynamics of a standard residual network, left, and invertible residual network, right. Both networks map the interval -2 to 2 to 1, a noisy x cube function at half depth. Okay, at half depth there's x cube. So if the input is -2 to 2, so this is -2, this is 2. Cubing will be, cubing. Wouldn't this be this must be less than 1, right? If at the end is gonna be squished, if it's gonna get squished, then it's just must be cubing less than 1 makes it squished. Huh. So this is halfway. This is halfway, right? This is halfway. That's a complete change of behavior. Like this is halfway. Yeah, so this guy, wow. Okay. Noisy identity function at full depth. Invertible resonance describe a bijective continuous dynamics, while regular resonance result in crossing and collapsing paths, circled in white, which correspond to non-bijective continuous dynamics. Due to collapsing paths, standard resonance are not a valid density model, of course, because now density is being collapsed into the volume is not now being collapsed. Yeah. Okay. This approach allows unconstrained architectures for each residual block, while requiring a Lipschitz constant smaller than 1 for each block. Yeah. We demonstrate that this restriction negligibly impacts performance while building image classifiers. They perform on par with their non-invertible counterparts on classifying MNIST Cipher 10 and Cipher 100 images. We then show that how Irisense can be trained as a maximum likelihood generative model on unlabeled data. To compute likelihoods, we introduce a tractable approximation of the Jacobian determinant of the residual block. Like FF Fjord, Irisense flows have unconstrained or free-form Jacobians, allowing them to learn more expressive transformations than the triangular mappings used in other reversible models. Our empirical evaluation shows that other models relied on mappings that are triangular, so that the determinant is always just the multiplication of the diagonal. So they don't use the full covariance matrix, but rather just a triangular one, so that the determinant is tractable, which is n squared is usually not tractable. So, but triangular one is tractable, which is just a multiplication of the product of the elements of the diagonal. Okay, because you need the determinant in the change of variables. Yeah. Our empirical evaluation shows that Irisense perform competitively with both state-of-the-art image classifiers and flow-based generative models, bringing general-purpose architectures one step closer to reality. Reality? What's reality? Reality meaning like, as in, what is reality? As in, Fisher Code, GitHub, yeah, Jacobson, Invertible Resonant. Sure. There is a remarkable similarity between resonant architectures and Euler's methods for ODE initial value problems. So, starting from XT, you generate, yeah. So this G generates a step from XT, and you get XT plus 1. Or if your step is homogeneous, you have the derivative, so f of theta gives you the slope, and slope times the step, you get the next, yeah. Where xt represents activations or states, t represents layer indices or time, h greater than 0 is the step size, and g theta t, so parameterized by theta t, is a residual block. This connection has attracted research at the intersection of deep learning and dynamical systems, and they cite all this stuff with their own paper here. However, little attention has been paid to the dynamics backward in time. So in backward time, yeah, you're subtracting. Yeah. Which amounts to the implicit backward Euler discretization. Yeah. In particular, solving the dynamics backwards in time would implement an inverse of the corresponding resonant. So here it still says, okay, you want at the beginning. So if you're here and going and integrating steps and coming here, if you're going back, you want the step that took you from here to here. Now when you're coming back, you say, okay, I want the same step that took me there, but so let's say no, okay, let's say you're integrating here. When you're integrating, you have the value at the current moment, right? X of t, and you generate let's say you generate a step, you generate a slope and multiply with a step. Let's say it takes you here. Okay. Now you have the value here. You generate a step, it maybe takes you there, then there, then there, and then there. But now, once you're here, and you don't have the path here, once you're here, how do you go back? If you try to go back, you're here now, I try to go back, but then you say, okay, in order to go back, I need to subtract exactly the step that took me from the previous step to here, right? I need to subtract this step. But in order to generate this step, I need to know the actual value that I'm going to arrive in there. So this is the chicken and egg situation. You're here and you want to know the step that you want that takes you you want to go a step back, but in order to go a step back, you need to know the actual location that you are going to step back to in order to generate the actual step that will take you back. So it's which amounts, so unless there is an inverse, unless there is an inverse that reliably we can say, let's say this is a step, so the slope at time t is equal f of theta at time t xt. Okay. Let's say if it's invertible, then we can say this whole thing would be invertible. Yeah. This whole block will be invertible. Yeah. Yeah, I have this. I want x of t. So this whole block, let's say this whole block is capital Q of x of t, right? So this whole block would have to be invertible. So Q inverse of xt plus 1 is equal to x of t. Yeah. This whole block, yeah. This whole residual block has to be invertible. Not just this, yeah. Only if it is invertible, then you, knowing where you are now, while you're coming back, knowing where you are will give you where to step back to. Right. In particular, solving the dynamics backward in time would implement an inverse of the corresponding resonant. The following theorem states that a simple condition suffices to make the dynamics solvable and thus renders resonance invertible. Theorem 1. Sufficient condition for invertible resonance. Let f theta from d to d with f theta being f theta 1 up till f theta composed up till f theta t denote a resonant with blocks f theta at time t is identity plus some step, then some slope, generator, then resonant f theta is invertible if the Lipschitz of each slope is less than 1 for all the time steps from all the layers, where lip g theta is the Lipschitz constant of g of theta. Okay. Lipschitz is the, like, if they have two inputs, x1 and x2, the difference between them should be smaller than, the difference between the output, let's say we pass in x1 and you pass in x2, is it squared? I think it's squared. The difference squared is less than or equal to L, the difference in the input, squared. So basically, the functions cannot diverge too. So the divergence in the output is bounded by L times divergence in the input. Yeah. So the functions could not take them apart more than they already are bounded by L. Yeah. So this is the Lipschitz, I think. Note that this condition is not necessary for invertibility. What? Oh, it's sufficient. Yeah, it could be invertible, but not could be invertible but not Lipschitz. Yeah. But it's sufficient to make it, While enforcing Lipschitz of G less than 1 makes the resonant invertible, we have no analytic form. Wait. Note that this condition is not necessary for invertibility. Other approaches rely on partitioning dimensions or autoregressive structures to create analytic inverses. While enforcing Lipschitz less than 1 makes the resonant invertible, we have no analytic form of this inverse. However, we can obtain it through a simple fixed point iteration. See algorithm 1. Note that the starting value for the fixed point iteration. While enforcing Lipschitz less than 1 makes the resonant invertible, we have no analytic form of this inverse. we don't even have a genetic form for, well, we have the like this neural network structure. However, we can obtain it through a simple fixed point iteration. See algorithm 1. Note that the starting value for a fixed point iteration can be any vector because the fixed point is unique. However, using the output y equals x plus gx as the initialization, x0 is y, is a good starting point since y was obtained from x only via bounded perturbation of the identity. Well, only if you... Yeah, because of the Lipschitz. From the Banach fixed point theorem, we have... So I think this is where you say x is equal... I think here they use g. Xt plus 1 is equal to xt plus g xt. Yeah. So the difference between at 0 and at n is bounded Lipschitz g to the n over 1 minus Lipschitz g times between 1 and 0. Thus convergence rate is exponential in the number of iterations n and smaller Lipschitz constants. So here, if we start this, so this is actually, this is going to be x1. Anyhow, it's less than, yeah, so this is exponential. Thus, convergence rate is exponential in the number of iterations, and smaller Lipschitz constant will yield faster convergence. We want this. We want xn to reach I think this is here, this is the inverse. And these are, yeah. I think this is the inverse. So that, yeah, convergence is... So the x at nth iteration is close to the inverse, bounded by this Lipschitz, but this Lipschitz is exponential. So that means, yeah, that means thus convergence is exponential. Okay. Additional to invertibility, a contractive residual block also renders the residual layer by Lipschitz. Additional to invertibility, a contractive residual block also renders the residual residual layer by Lipschitz. Lipschitz constants of forward and inverse. Yeah. So we said, okay, so that makes wait, we only started if it's Lipschitz. Yeah, only if it's Lipschitz less than 1, then it's invertible. Sorry, not only if, but if it's Lipschitz less than 1, then it's invertible. It's not necessary but sufficient. And if it's invertible, then it's by Lipschitz. Lipschitz constants of forward and inverse, let fx x plus g with Lipschitz equals L less than 1 denote the residual layer Lipschitz of g. Then it holds that Lipschitz of f is less than 1 plus L, and Lipschitz of f minus 1 is 1 over 1 minus L. Hence, by design, invertible resonance offers stability guarantees for both forward and inverse mappings. In the following section, we discuss approaches to enforce Lipschitz condition. Yeah, so yeah. Since 1 minus L wait, 1 over 0.9 okay, but that means it's bounded by it is Lipschitz, but it's not less than 1. Okay, never mind. Satisfying the Lipschitz constraint, we implement residual block as a composition of contractive nonlinearities, ReLU, ELU, TANH, and linear mappings. For example, in our convolution networks, G is equal to where WI are convolution layers. Think there's no bias? Yeah. Lipschitz is less than 1 if the spectral norm, yeah. Spectral norm is less than 1. Spectral norm is the largest singular value, yeah. Where, yeah, denotes the spectral norm. Note that regularizing of the spectral norm of the Jacobian of G. Why are we talking about the Jacobian of G? Note that regularizing spectral norm of Jacobian of G only reduces it locally. and does not guarantee the above condition. Thus, we will enforce for each layer. Yeah. A power iteration on the parameter matrix, as in Miyato et al., approximates only a bound on the spectral norm of the weight matrix instead of the true spectral norm. If the filter kernel is larger than 1 by 1, yeah. For details on the bound, hence, unlike Miyato, we directly estimate the spectral norm of W by performing power iteration using W and W transpose as proposed. Yeah, the power iteration yields an underestimate. Using this estimate, we normalize. Okay. So we get the estimate, and then we divide C over sigma I. If it's less than 1, we divide by it. Otherwise, we leave it alone. It's already less than 1. The high parameter C less than 1 is a scaling coefficient since since theta I is an underestimate. Wi is not guaranteed. However, after training, Sedgi et al. Offer an approach to inspect exactly using SVD on the Fourier transformed parameter matrix, which will allow us to show Lipschitz holds in all cases. Okay. Generative modeling with Irisense. So the whole idea is okay. The whole idea is using the spectral norm to using the spectral norm. Generative modeling with Irisense. Okay, so the rest is dedicated to how to actually do generative modeling. Yeah. This follows directly for the inverse. Consider that fx spectral norm is x minus y plus gx minus gy, and you have x minus y minus gx plus gy. This is bigger than, definitely bigger than this. Yeah. Okay, and since this is -1, doesn't affect the norm. GXGY is they are bounded by Lipschitz. Yeah. Where we apply the reverse triangular inequality in 7 and apply the Lipschitz constant of the G. Okay. Yeah, so here you get the inverses. X is f-1z and y f-1w. So we get, yeah. Okay. Generative modeling with Irisense. We can define a simple generative model for data XRD by first sampling Z from a certain distribution where Z is an RT, and then defining X equals some transformation of Z for some function, yeah, X, D, and E. If phi is invertible, and we define f equals the inverse, and then we can compute the likelihood of any Z under the model using the change described formula. The log likelihood of X in X distribution is, well, find the Z that this inverts to it, and yeah. So this is for the change of variable. Where g f x is the Jacobian of f evaluated at x. Models of this form are known as normalizing flows. They have recently become a popular model for high-dimensional data due to the introduction of powerful bijective function approximators whose Jacobian log determinant can be efficiently computed or approximated. Since Irisenets are guaranteed to be invertible, we can use them to parameterize f in equation 3. Samples from this model can be drawn by first sampling z and then computing f, using the inverse with algorithm 1. Algorithm 1. Algorithm 1. Inverse of Irisenet layer via fixed point iteration. Output from residual layer y. Contractive residual block and number of fixed point iteration. Yeah. Init make x0 equals y, and then for I0 to n do, yeah, fixed point. Okay. Yeah. So this formula basically says you have a real variable. Let's say this is a real distribution like this. Okay. And you have a Gaussian distribution. You know, if you sample Z from here, you know its density. Okay. Or the PDF. So PZ of Z, you know it. But when you map, you have a bijective function phi that maps every dot here to a certain dot here. Certain regions can map to a wide range of regions, right? Wide range of regions. So this stretching that happens, stretching or contracting, is modeled with the Jacobian, basically, how each variable here, how it's stretched across all the variables there, all the dimensions there. So all the dimensions there, how they are stretched, all the dimensions there. So partial xi, partial zj, right? So the term of the Jacobian gives you the volume of the stretch, how much volume here or density here, how represents how much density there. Yeah. So this is what this basically says. In figure 2, wait, what? In figure 2, we show an example of using INET to define generative model on some two-dimensional datasets compared to GLOW. Scaling to higher dimensions. While the invertibility of Irisense allow us to use them to define a normalizing flow, we must compute to evaluate the data density under more model. Computing this quantity has time cost of So the problem here I'm facing us is basically RD is still RD. And that's problematic because if we want to reduce the entire image in Z in RK, where K is less than the dimensions of the image, which is assuming it's D by D, we can't use invertibility. Anyhow, yeah, I'm not gonna entertain this paper anymore. Well, this is not exactly what I'm looking for, but maybe I'll come back to it later on because I will need some invertibility in some location, but I guess I understand. I don't need to estimate the density, but I just need the invertibility in going from one place and returning back to it. Um, yeah, but okay. Okay, so that's the end of the stream. So all we saw that all you need to do is to basically spectral normalization, make sure that um, the spectral norm for the weight matrix for any of the convolution is less than um, some C, which is less than 1, by dividing, by multiplying this, and this is the estimate using WI and WI transpose. They provide the paper to return to. Okay.